So negative edge trigger. So what are the advantages of this? It is very simple to implement. Only 2 transistor and 2 inverter can give us a dynamic 1-bit resistor or flip-flop. So the circuit overall consumes very less power and also less area. It's a very compact design. But the problem here is the robustness problem. As we pass one, it will be distorted here. And it is a dynamic circuit. This node will be floating, this node will be floating. When in a floating node, any voltage is vulnerable. But if it experiences a threshold voltage drop while passing, it will be already distorted. So if you have a distorted signal reduced by a threshold voltage while in floating state, it becomes very vulnerable to noise. So this circuit is very fast, very area efficient. It will consume less power, but it will be very vulnerable to noise because of the NMOS transistor switch. And it is floating state. So, what can we do to avoid the threshold voltage dropping in NMOS? We can use 2 transmission gateway switch, right? This will be a dynamic floating node, this will be a dynamic floating node A and B, but the switches will be transmission gate instead of NMOS transistor, so it will not experience the threshold voltage drop. So you will have full strength signal, but it will still in floating state, it will have all the problems of dynamic floating node. But in NMOS only implementation, in addition to having all the challenges for a dynamic circuit, floating dynamic node, it will experience a threshold voltage drop. So if we compare NMOS only implementation with the transmission gate based implementation, this will be more robust. However, it will take some extra area because of the transmission gates are bulkier than a single NMOS transistor. So one of the problem, as we repeatedly mentioned in case of synchronous latch flip-flop and resistor, is the clock overlapping problem. Because inside this circuit we need clock and clock bar together in every step. So between clock and clock bar there will be at minimum an inverter delay. So when clock is going down or going up, clock bar will not go up or down at the same time. So there can be 2 potential overlap. One, clock is going 0. Clock bar should be at the same time going to 1, right? They are opposite. But when clock is going 0, clock bar will go to 0 after some time. So there will be a tiny period of time both clock and clock bar will be 0 and 0. Similarly, there will be a tiny period of time when both of them will be 1, 1. So it is called 0, 0 overlap. It is called 1, 1 overlap. So the way it is implemented, this is on for clock 0. When this is on, T1 is on, T2 must be off. But during the 0, 0 overlap, both of them will be on simultaneously. So what do we have to do? That 0, 0 overlap, this one should not remain on long enough for a new signal to come here and destroy the value. Because when this one is copying a value, this one should be maintaining its previous value at node B in floating state. But for 0, 0 overlap, for a tiny period of time, both switches will be on. So if the delay as it signal D moves from A to D, how fast it can move, it depends on the delay of transmission gate T1. And then from A to B, how much time it will take? Delay of inverter 1 and delay of transmission gate 2. So if this delay and this delay, these two are equal, let's say assume that they're equal, but T overlap must be less than any of this delay, so that by the time it crosses, the overlap period is gone and this one is off. so signal cannot travel from here to here, right? So the T overlap can be tolerated, 0-0 overlap can be tolerated, but we have to make sure that this overlap time is less than this delay or this combined delay. So that by the time the signal comes here, it is already turned off. Similarly, we can basically do the similar analysis for 1-1 overlap. In general, for 1-1 overlap or for 0-0 overlap, we have to make sure that the hold time is greater than this one. For this particular case, the hold time should be greater than 1-1 overlap, because in 1-1 overlap, it will be, both of them will be off. So at this different node, you should be holding. If both of them are off, no new value can go in. Both will be in hold mode. So that hold mode should be long enough to overcome that T overlap time, because 1-1 overlap time, because during that time, both will go into hold mode, no new value can come in. But typically the operation in master slave latch flip-flop, the way it is organized, if this one is latching or copying new value, this one will be hold mode. If this one is copying a new value from here, this one will go to hold mode. But for 1-1 overlap, in this particular resistor, both will be in hold mode for some time. So that during that hold mode, nothing will happen. So that hold mode should be long enough to override the 1-1 overlap time. So these are some restrictions on dynamic latch in terms of clock overlap. So this gives us a value. What is the limit of overlap time we can tolerate inside any dynamic resistor or flip-flop without contaminating the value. And we already know this. One way to overcome or make the dynamic logic circuit or dynamic flip-flop resistor little bit more robust is to make it pseudo-static, that we are not disconnecting the loop. So this node will not be in floating state, or this node will not be in floating state because there is a continuous loop, right? But this node may be in floating state. So one of the node is in, sometime it will be floating, but sometime it will have the complete connection. So that way we are making it kind of a pseudo-static by making this switch much stronger than this feedback inverter, but it will have then ratio problem. Then we have to make sure that these transistors are much larger and stronger than the transistor used for this inverter. So up until now we have seen all the flip-flops and resistor we have seen in this lecture 7, and all the resistor or latches flip-flops we have seen in lecture 6. One common thing is, in every static and dynamic latch so far we have seen, they require 2 clock phases, clock and clock 1. And repeatedly we have highlighted there will be an overlap time, 0-0 overlap or 1-1 overlap, because it will be impossible to make the delay difference between clock and clock bar 0. You cannot make that when clock is going up, clock bar should be going down simultaneously. So you cannot avoid the delay difference between clock and clock bar in 2-phase resistor. 2-phase means you need clock and clock bar both. So next we are going to explore, can we design a latch or resistor or flip-flop that can be operated only by one phase of the clock, either clock or clock bar, not both. But as you see in every slide, every circuit, dynamic or static, latch, flip-flop and resistor we have explored so far, always you need clock and clock bar. And that will always lead to this 0-0 and 1-1 overlap problem, and it will impose lots of additional constraint. So if we can design a latch or resistor or flip-flop by using only one phase of the clock signal, then we call it true single phase clocked resistor. A resistor or a flip-flop that will require only one clock phase, either clock or clock bar, not both at the same time. So now, fundamental to any bistable resistor or flip-flop, what we have? We have a loop of two inverter if it is a static circuit, static latch or a static flip-flop. We have a just open chain of two inverter if it is a dynamic. I will borrow your pen again. So, latches, flip-flop and resistor, sequential circuit in general. So, sequential circuit in general can be of static and dynamic. The fundamental building block of static is a loop of two inverter. So every node will have a back-to-back positive feedback connection, so at any point they will not be floating. The fundamental building block of a dynamic latch or flip-flop or resistor is just a chain of two inverter, not a closing loop. So if the input is disconnected, this node will be floating. If there is a switch, if this switch is off, this node will be floating. Typically we do have a switch here, we do have a switch here, right? So once again, all you need to remember, the fundamental building block of any static latch flip-flop or resistor will be a loop of two inverter. For dynamic latch resistors and flip-flop, it will be series of two or chain of two inverter connected without having a loop. So TSPC, two single phase clock resistor, is a dynamic resistor, dynamic flip-flop. So it will have a chain of two inverter. That means it will be made just a series connected to inverter open-ended. So if you look at this circuit, what do you have? The first one, forget about this clock. It is, first one is an inverter, right? If I draw the circuit here, what I have? This is an inverter, right? Second one is another inverter. Right? Here, two inverter connected back to back, and this is the final output, right? So now, if I insert a clock signal inside any logic circuit, it becomes clock control. So now I inserted a clock here in the first inverter, another clock here in the second inverter, right? So what happens here? So this is my output. So when clock is 1, in this case, this transistor is on, right? That means this node is shorted with this node, it converts to this inverter, right? When clock is 1, this transistor is on, it is shorted, so it converts to the second inverter. Now I can apply an input here, this will get an inverted output here, and that input will come here, right? 1, 0, 1, 0, 1, 0. And if I disconnect this input or turn off the switch, what will happen? This is open, this node will be maintaining its whatever value you have sent in floating state. If this clock is on, this will be also carrying its value in floating state because it's disconnected from one side. So it is a dynamic node, but it is dynamic latch or resistor, but it is controlled by clock signal. In the first circuit, we have used two NMOS clock signal, both operated by clock. We can also make this circuit controlled by PMOS clock. So if I use a PMOS clock here, then I have to put it with this PMOS. I have to put with this PMOS. When clock is 1, clock is 0 here, clock is 0, this PMOS is on, So this PMOS and short with this NMOS, it gives me first inverter. When clock is 0, this PMOS is also on, so this is short, this gives me second inverter. But when clock is 1, this is open, this node will be floating, this node will be floating. But in both cases, I am able to store a new value from D to output, input to output here in dynamic floating state by controlling the clock signal. So what will happen in this case, if clock is 1, this inverter is complete, this inverter is complete. So I have a complete chain of inverter. By applying a new value here, I can set a new value here. That means when clock is 1, the latch is in transparent mode, it can copy a new value. When clock is 0 here, this is off, this is here, this is disconnected, this is disconnected. No matter what you do, nothing will happen here because it is disconnected. So it will be maintaining its previous value in its floating state, so it will be in hold mode. So for this one, clock is 1 means transparent mode, copy new value. Clock is 0 means it will be hold mode, it will be maintaining its previous value in floating state. Here it is opposite. Clock is 0 means it is transparent, copy a new value. Clock is 1 means it will be holding its own previous value. So this one is a positive TSPC because when clock is 1, it can copy a new value. This one is a negative TSPC because when clock is 0, it can copy a new value. But in both cases, we are using only the clock signal. Nowhere in any other circuit we use the clock bar, right? One using NMOS, one using PMOS. So we are getting both positive and negative single phase resistor. So we already explained the operation. So if you ask to implement any TSPC positive, then this will be the one. TSPC, negative TSPC will be the one. So it is a dynamic resistor. Exactly like this one, right? It's a dynamic resistor exactly like this one. Only thing is this inverter and this inverter, they are clock control. So it is a memory device, but dynamic memory device. But there is a one distinct feature of TSPC resistor is that this circuit can be also used as a non-inverting logic circuit. This circuit can be used as a non-inverting logic circuit. How is that? Before understanding the operation of that, let me quickly look at the CMOS circuit. CMOS circuit has two blocks, right? And this can be n number of input. This is pull-up network. This is pull-down network. This is VDD. This is ground. This is my output, right? This is the CMOS. So it can be n number of input. Let's say n equal to 4. So it's a 4 input CMOS gate. However, CMOS gates are by default inverting. If I implement an n, I will get an NAND. Right? What if these all four, let's say there are 4 connections. All 4 connections are tied to one input node. Then it becomes a single input, single output. So if you apply a 1, that one will go to all 4 inputs. Then this pull-down network will be on, this pull-up network will be off, output will be connected to ground, 0. So it will produce a 0. If I apply all zeros here at the input, pull-down network will be off, pull-up network will be on, then it will give me a 1. So a short-circuited CMOS gate is nothing but an inverter. So what is the conclusion? if you apply same inputs to the all input terminal of a multi-input CMOS gate, it acts like an inverter. Whatever you apply here in all the input terminals, it will produce this inverted output. So, a CMOS logic gate, any CMOS logic gate can be used as whatever the logic function is intended for. Also, it can be used as an inverter. All you have to do, apply same input to the all input terminal, then at the output you will get just opposite inverted of the input you applied, right? So this is basically the biggest advantage of CMOS logic gate, that it can be used as any general purpose logic function. Let's say if you implement something AB plus C, whatever you get, it can be used for this one. In that case, A, B, C will be all unique inputs. But if you make A, B, and C all equal to 1, output will be 0. If you make all of them equal to 0, output will be 1. That means a short circuit at the input, or applying same input to the all terminals will give this as a, you can use it as an inverter. So, why I am explaining that? Because to use this TSPC as a memory circuit, we need a chain of 2 inverters. Clock control or unclock control, right? We need a chain of 2 inverters. Now, if I change this structure of this circuit like this, first step, instead of an inverter, let me use as a clock control CMOS gate, followed by a clock control inverter. This can be used as a uninverted logic gate, because this is nothing but a clock control CMOS gate followed by a clock control inverter. So if you apply a 2-input NAND gate here, final output will be a 2-input AND gate, because a NAND followed by an inverter is AND. That's what we have did, right? 2-input NAND gate means 2 NMOS in series, 2 PMOS are in parallel. And I inserted a clock to make it clock control, followed by a regular clock control inverter, right? So now, this whole circuit, inside this box you can implement any function. This whole circuit is nothing but the final output is a 2-input AND gate. It's an uninverted 2-input AND gate. Now, so it can be used as an uninverted logic function. But now I apply same input to input 1 and input 2. Let's say I want to copy a 1 here. If I want to use it as a memory, I want to store a 1 here, what I will do? I will apply 1 to all of them. Tie them together. I will apply 1 to all of the inputs, both of the inputs. Then it will produce a 0 here, because by default, for same input, it is an inverter. This 0 will set the value of this inverter as 1. So whatever you want to store, you apply to all the inputs here, you can store that at the output. So it is acting as a memory circuit, also it is acting as an uninverted logic function. So that is a unique feature of TSPC logic, which can be used for dual purpose. Same circuit sometimes can be used as a memory storage element. You just apply whatever you want to store, 0 or 1 to every input, it will be stored at the output. Or you use every input as a unique input like A, B, C, D or whatever, then you get the output as a function in uninverted form. So this is a unique. So now I can give you any random function like this, and I can ask you to implement it in TSPC, positive or negative. So this I am showing here CMOS clocked CMOS gate with a clocked CMOS inverter, but with positive clock signal it will be in transparent mode, negative 0 clock signal it will be in whole mode. I can basically implement same structure here. Only thing, this inverter will be removed by pull down, this inverter will be removed by pull up network. Right? So you should be able to implement any random function in positive TSPC and negative TSPC. Do some practice at home. So I will finish with that because as I said I have to run to a meeting, but I think on TSPC there is just one slide left. Let's finish that. So in all of this implementation, there are two clock signals required, whether you go by this one or that one. First stage and second stage, two clock signal, right? So circuit designer, they always try to minimize the number of transistors required to implement each bit. So that one design group explored, how about not having a clock at all in the second stage? Only let's keep the clock in the first stage, first inverter. So they tweak the connection a little bit. So it's an inverter, right? When clock is on, so as you can see, for the second inverter, they did not tie it together. They put one connection on the top of the clock, one connection at the bottom of the clock. When clock is 1, this is short. Then this node, all are short. So it is two inverter, one after another, right? When clock is 1, they are together. Now if I apply a 0 here, 1 here, then this will be on. Clock will be on because I am trying to copy a 1 from here to here. When 1, it will turn it on. Clock is on, it is on. So this node will be connected to ground. So this will become 0. This 0 will turn this on. This 0 will keep this off. So it will be connected to VDD, will become 1. So 1, 0, 1 I am getting as it is because with clock equal to 1, this is short. So without the second clock, I can still store 1 without any problem. But the issue will come a little bit of distortion. Let's say I want to store a 0 here, so I will apply 0 here. 0 here will turn this on, will make this node, intermediate node to 1 because 0 will turn on PMOS, it will connect this node to VDD. Now, clock is on, they are connected. When this is 1, this should be on, intermediate node. When clock is on, this is short circuit, right? This should be on because with 0 here, I should get 1 here, I should get 0 here. To get 0 here, I have to connect it with the ground. To connect it with the ground, I have to turn this transistor on, I have to keep this transistor off. Right? With 0, this is on, this is connected to VDD, so this will be off anyway. But when I turn this 1 into 1 and this clock is 1, A should also be 1 to turn it on strongly. But this one, connection to VDD, that signal, when it travels to node A, through this clock NMOS transistor, what will happen? It will experience a 1 threshold voltage drop. So the maximum voltage node A will get is equal to VDD minus threshold voltage of the clock transistor, right? So the top of the clock transistor, it will have VDD because it is connected to VDD. But bottom of the clock transistor at node A, the maximum voltage that can go up to VDD minus threshold voltage of the clock transistor. So the second NMOS transistor, which is supposed to connect output to the ground, at the input, the maximum voltage it is getting is VDD minus VTN. So it will not be strongly on. Because to turn it strongly on, we have to basically apply the maximum voltage at the gate, which is VDD. So there is one problem, the circuit will go down very slowly, or this node now is already distorted, and we are talking about dynamic circuit, floating node, then if this node is distorted in between, then noise and any other thing can disturb this intermediate node A easily. That will affect the on-off condition of this transistor. That will affect your integrity of the output signal, right? So it will add some vulnerability, some noise problem by removing this clock signal, but still it is logically it works. So if your circuit is very sensitive, that we cannot tolerate this type of distortion in any intermediate node or input node or final node, then we should not eliminate this clock. But if your circuit is not that very sensitive, that this type of distortion is okay, then we can eliminate the second clock signal to make the circuit simpler. So why if the circuit, the elimination of clock makes it vulnerable, then why you eliminate the clock? Because when we are talking about megabytes and terabytes of memory bits, if you can remove one transistor per memory bit, you are talking about 1 billion savings, right? For a 1 terabyte, think about each one of them is storing only 1 bit. When you are talking about terabytes of memory, if you can remove one transistor from each bit, then you are talking about savings of billions of transistors. That's why memory circuits are intentionally designed with lowest number of transistors possible. They ignore all the vulnerability. They add some additional protective circuitry around memory core to take care of the noise problem. That's why DRAM became so popular. In lecture 10, we will see why DRAM replaced static RAM SRAM overnight from all laptop and most of the handheld device, because the number of transistors. DRAMs or this type of design, they make the circuit very vulnerable to noise, even knowing that they use that more vulnerable, simpler design to save area, the number of transistors in a chip, because the memory requirements from app to app is increasing exponentially. So from the same space, we need to have more memory bits. So continue that. So right now I have to leave for an important meeting.
Sir, when you take class in evening, can you please explain this? When you are giving input signal 1 or 0, what is
Yeah, I will actually, we will start from here. So today our target, lecture 8 is only 7 or 8 slides. So today our target is to finish lecture 7 and 8 because we have to keep some time for quizzes, and also
Next class we have a quiz.
Thursday we'll have a quiz on lecture 6 and 7. There will be a combined quiz on 6, 7 and 8. Those are related.
6, 7, 8.
6, 7 and 8 on next Thursday. Okay. Yes.